Hi there guys, Mr. Pope from Wilmington Grammar School for Boys, and we're going to be looking at some algebraic methods. First one I wanted to look at was the factor theorem. And essentially it's kind of linked in with the remainder theorem as well. So let's have a little tack in. It's kind of the same thing, just the application is slightly different, I suppose, well, let me just write it down. So if I've got a function of x, like so, and I want to solve when that function equals 0, then if I find one solution of that function, let's call it a, so that when I plug a as an input, so this is actually a solution or a root, then this implies, and it's a two-way thing, so one implies the other and vice versa, that x minus a is a factor of f of x. Okay, this is quite powerful. So, for example, let's suppose I had x squared minus 7x plus 12 equals to 0. Well, if I let x equal to 3, so if I let this be my f of x and I want to solve f of x equal to 0, then 3 squared minus 7 lots of 3 plus 12, does that equal to 0? Well, 3 squared is 9, minus 7 threes is 21, plus 12, that does equal to 0. So that means if x equals 3 is a solution to this, that means x minus 3 is a factor. So x minus 3 times by something will give x squared minus 7x plus 12. And you can probably guess what's going to happen. X times what will give the x squared, that must be x. And minus 3 times what must give a positive 12, that must be minus 4. And you can see how that works out, because minus 3x there and minus 4x there will indeed give the minus 7x. Now this seems a bit dumb for quadratics, which you should be fairly familiar with by now, but the whole point of this factor theorem is that it applies for any function of x. It doesn't matter if it's trigonometric, exponential, cubic, nonlinear, a non-elementary function, it works. Okay, so this is quite important. We're going to be going through a couple of things with this. The remainder theorem is that the remainder theorem is very similar, but it's that when you input b, then this will output a remainder into my function. What does that mean? So where r is a remainder. What does that mean? Well, that's the remainder when divided by x minus b. And we're going to be talking about algebraic long division in a second. Just to remind you what a remainder is, let's suppose I divide 8 by 3. What is the remainder there? Well, 8/3 is the same as 6/3 plus 2/3, right? Because 6 is the largest number lower than 8 that can be divided by 3, and 6/3 is 2. So it's 2 and 2/3. So in primary school, you might have had to do something like this. Let's say you've got 8 divided by 3, and 3 goes into 8 2 times, and there's 2 left over, so you'd put remainder 2, right? This 2 up here is the remainder. This 3 down here is what's called the divisor, right? Because we were dividing by 3, that's the divisor. Okay, now we're going to look in a second, what does it mean to do algebraic division? How do you do that? Well, essentially the factor theorem, remainder theorem, that's it in a nutshell. I'm just going to do a couple of examples in a second. But let's suppose I want to get into this concept of what is algebraic long division. So, I don't know, let's say I had x squared minus 7x plus 12 again, but this time I want to divide it by, let's say, x plus 5. Okay, how can I deal with this? Well, you treat it like division that we've seen so far. So x squared minus 7x plus 12, and we're dividing by x plus 5. Okay, so the technique is, what do I have to multiply the x by to get an x squared? Well, I have to multiply it by a single x, right? Because x times this x will give the x squared. Now what I have to do is multiply x by all of this thing, x plus 5. So x times x plus 5 is x squared plus 5x. And then once you've done that, you need to subtract terms. So x squared minus x squared, they cancel. And minus 7x minus a 5x will be minus a 12x. You bring the next term down, so it's plus 12, and then you carry on. So the next question becomes, x times by what will give minus 12x? Well, at the top, that needs to be a minus 12. And now we redistribute this minus 12 into here. So minus 12 times x is minus 12x, and minus 12 times 5 is minus 60. We do the subtraction again, so minus 12x and minus 12x cancel, and 12 minus minus 60 is 72. And we've now reached the end, so we stop. Right, now this 72, that is a terrible choice of colour, this 72 is the remainder. Okay. The end result is called the dividend. It's what it's been divided up into. And this thing here is the divisor. It's divisor. Okay. I believe that's right. Okay, so what does this mean? This means that I can write x squared minus 7x plus 12 over x plus 5 as the dividend bit, which is x minus 12, plus the remainder, which is 72, over the divisor, the thing that I've just done by, which is x plus 5. So in actual fact, this left-hand side is the same as this right-hand side. And you're probably thinking, okay, how is this particularly useful? Well, suppose I wanted to plot the graph y equals that thing. It's actually a lot easier to plot the graph on the right. Why is that? Well, because for really large values of x, as x tends to infinity, you're going to be doing 72 divided by a large number. So this term cancels out to 0. So with large values of x, this tends to approximate the line y equals x minus 12. It tells you various other things. For example, this point here, x can't equal to minus 5, because that's a pole, and so on. There's various other different things going on here. But generally speaking, when it comes to sketching graphs, which we'll do at some point, this is more of a useful. This stuff is more of a useful form to put things into, especially when it comes to more complicated questions. So, just to see if that makes sense, I divided by x plus 5. So that means if I substitute, well, if this thing equals to 0, what must x be? Well, x must be minus 5. So I'm claiming that if I substitute minus 5 into there, that will give me the same remainder, which is 72. Let's check. So this top part was x squared, so minus 5 squared, minus 7 lots of the minus 5 I'm inputting, plus 12. Well, let's deal with that. Minus 5 squared is 25. Minus 7 times minus 5 is plus 35, plus 12. 35 and 25 is 60. 60 plus 12 does equal 72. Okay, so look what this is saying. If I divide x squared minus 7x by 12, x squared minus 7x plus 12 by x plus 5, I can either do algebraic long division and find the remainder, 72, which also shows that x plus 5 is not a factor, or I could just do the shortcut and substitute in minus 5, because that's what happens if you let x plus 5 equal to 0. And if the remainder is not 0, it's not a factor, and you can work out what the remainder is quite quickly. Now, you need to know both methods, because sometimes you might have to solve simultaneous equations where long division wouldn't necessarily be possible or useful. And that's pretty much it for the first half. So I just want to go through some examples. So again, if you understand so far, pause the video and give it a couple of minutes or so. Try it yourself. If not, I'm going to go through the answers now. Okay, find the remainder when f of x is divided by x minus 3. Well, same deal. We set this equal to 0, so that's clearly when x equals 3. So the remainder is when we substitute 3 into this. So I've got 3 lots of 3 cubed, minus 5 lots of 3 squared, minus 58 lots of 3, plus 40. Well, 3 cubed is 27 times 3 is 81. 5 squared is 9, 3 squared is 9, times by 5 is 45. 58 times 3, I believe, is 174, plus 40. Well, what have we got here? We've got 81 and 40, which is 121. And we've got 45 and 74, which is going to be 179 plus 4, it's 219, isn't it? So we've actually got the negative of 219 minus 121, so that's 8, can't do, it's a 9. So I believe the remainder is negative 98. Where's my calculator? There it is. Let's just double check. Don't be making a mistake at the last minute. But I'm pretty sure that's right. So what have we got? We've got 3 lots of positive 3 cubed minus, daisy, minus 5 lots of 3 squared minus 58 lots of 3 plus 40 minus 98. Okay, confident in that answer. Okay, given that x minus 5 is a factor of f of x, find all the solutions. Right, okay. So, if x minus 5 is a factor, this means this can be broken up into, well, let's think about it. The highest power is x cubed, so there must be an x squared in here. And since this is an x, this must be a 3x squared, because 1 times 3 would give the 3 for the coefficient. Next up, this is a minus 5. So this number term, minus 5 times what will give 40? Well, this must be a minus 8. Okay. Now, there's various things you could do. You could either compare the x squared terms, or you could compare the x terms. Doesn't particularly matter. What I'm going to do is the x terms, because it's probably the easier. So minus 8x, if I multiply these two things together, plus minus 5 times this should give minus 58. Well, clearly, what have I got to add to minus 8 to get minus 58? That's minus 50. So minus 5, and then this must be plus 10x for that to work. Okay. So that seems pretty legit. Let's just check the x squared components to see if that works. So to get the x squared, it would be 3x squared times minus 5. So we've got a minus 15 there, and then we're going to have a 10x plus an x, so we're going to have plus 10x squared there, plus 10 minus 15 does give minus 5, so that works. Okay, so if x minus 5 is a solution, let's check this thing over here. Does it factorize? Well, you can use your calculators to solve this if you really want to, but I don't like using calculators just because I like my brain being exercised. So let's check. B squared minus 4ac. So b squared is 100 minus 4 lots of a, which is 3, lots of c, which is minus 8. 4 times 3 is 12. 12 times 8 is 96. Minus minus makes that a plus, so that's 196, which is a square number. It's 14 squared. So this can factorise. So what two numbers add to 10 but multiply to minus 8 times 3, which is minus 24? I think that's going to be 12 and minus 2. So I can split this up into 3x squared plus 12x minus 2x minus 8, which is 3x lots of x plus 4 minus 2 lots of x plus 4. So I make that 3x minus 2 lots of x plus 4. And now once we've got it in this stage, it's quite easy. We can just read off that x equals 5, x equals 2/3, and x equals negative 4 are the three solutions. If I set all of these brackets equal to 0 and solve, so 3x minus 2 equals to 0 becomes 3x equals 2 divided by 3, x equals 2/3. Yeah, that's pretty elementary. You should be able to get that. So there's three solutions. It's a cubic. We found all of them. Hurrah. All of them were real. Okay, next question. So pause the video, give it a go yourself. Okay, where f of x equals 2x cubed plus ax squared plus bx minus 6, where a and b are constants. When f of x is divided by 2x minus 1, the remainder is minus 5. And when f of x is divided by x plus 2, there is no remainder. Okay, so what does it mean to divide by 2x minus 1? Well, if I set that equal to 0, then x must be 1/2. So what that's saying is when I substitute a half into this thing, it will result in minus 5. So let's start with that then. So I've got 2 lots of a half cubed plus a lots of a half squared plus b lots of a half minus 6 equals to negative 5. Well, if I add the 6 onto both sides, so that's a 1. A half cubed is an eighth, times by 2, so that's a quarter. Half squared is a quarter, so that's a over 4 plus b over 2. If I times everything by 4, I'll get 1 plus a plus 2b, be careful, and this is 4. And if I minus 1 from both sides, I get a plus 2b equals to 3. So that's one equation I'm probably going to have to solve simultaneously. And as I've said before, if there's two unknowns, 1, 2, you're going to need two equations, i.e. two useful bits of information, and they've given you the second bit there. When f of x divided by x plus 2, there's no remainder. So again, what must x be so that this bracket equals to 0? Well, x must be minus 2. And what that's saying is if there's no remainder, then f of x, or f of 0, must equal to 0. So again, sorry, not f of 0, lol. What is it? X is minus 2. So f of minus 2 equals to 0. So let's substitute that in and see what happens. So 2, well, we can skip bits. Minus 2 cubed is minus 8 times by 2 is minus 16. Plus a lots of minus 2 squared is 4a. Plus b lots of minus 2, which is minus 2b, minus 6, and that equals to 0. I've got, if I add 16 and add 6 to both sides, that's 22 equals 4a minus 2b, and I can divide everything by 2 to make it easier, to make 11 equals 2a minus b. Right. In actual fact, considering I'm looking at the other ones, probably not a good idea, because I can immediately eliminate for b, because if I've got this equation and this equation, I realise one of them is plus 2b and one of them is minus 2b. So if I add those two equations together, I'll get 4a plus a, which is 5a, minus b plus a 2b is nothing, and 22 plus 3 is 25. Clearly a is 5. Now if a is 5, I've got 5 here, plus 2 lots of what equals 3. Well, b is clearly negative 1. And just double check that into the other one. 4 lots of 5 is 20, minus 2 lots of negative 1 does indeed equal 22. So that's cool. So this is taking up too much space, so let's shrink this down. So my answer, my answer for A and B would just be a is 5, and b is negative 1. Factorise f of x completely. Okay, well let's write f of x out again just to remind ourselves. So it's 2x cubed plus a, which is 5x squared, plus b, which is minus 1 lots of x, minus 6. And I know that x plus 2 is a factor already because there's no remainder when you divide by that. So I know one of the brackets straight away is x plus 2. Now because this is a cubic, then it must be a linear times by a quadratic, i.e. a power to the 1 times by some polynomial to the power 2. Now I know that because that's 2x cubed, this has to be a 2x squared, and because this is a plus 2 and this is a minus 6, then that must be a minus 3 there. Comparing coefficients, well, let's do the x squareds. I've got 2 times 2x squared, which is a 4x squared, so I need 1 extra x squared, so that x in there, so that must be a plus x. I'll compare for the x coefficients to check this makes sense. So minus 3 times x is minus 3x, and 2 times x is plus 2x, and that will result in a minus 1, so that's fine. Okay, x plus 2 times by 2x squared plus x minus 3. Well, it actually wants us to factorise, so I don't need to set that equal to 0. That's just getting ahead of myself. So does this quadratic factorise? Well, the clue's in the question. It says completely, so we need to check. You know, this might not fully be it. So I'm going to skip the b squared minus 4ac bit. So if I've got two numbers that add to the middle coefficient, which is 1, and two numbers that multiply to the product of the outside 2, so 2 times minus 3 is minus 6, and I think those two numbers are positive 3 and negative 2. So I can rewrite this quadratic as 2x squared, and then using these numbers, I've got plus 3, lots of x, and minus 2, lots of x. See what I did with these two, and I split the x up, minus 3. And then I'm going to have, if I factorise the pairs, I've got x lots of 2x plus 3, and then I've got minus 1 lots of 2x plus 3 here. So it looks like this can be factorised as x plus 2 times by one of the brackets, which is 2x plus 3, that repeated bracket, and then the other bracket is just the minus 1 and x, which is x minus 1. So my final answer is x plus 2 times by 2x plus 3 times by x minus 1. And you can have them in any order, it doesn't particularly matter. Okay, right, again, pause the video, give yourself a shot at doing this. Should be getting the hang of them by now. Okay, when f of x is divided by x minus 2, the remainder is 1. When f of x is divided by x plus 1, the remainder is 28. Okay, same deal. This is, we're going to have to let x equal to 2 there. So when the whole thing equals 0, x minus 2 equals 0, so x is 2. If I substitute all that in there, 2 cubed is 8 minus 2 squared is also 8, plus 2a, which plus b, and that has a remainder of 1. So immediately we get 2a plus b equals 1 from the first one. And then x plus 1 equals to 0 means that x equals minus 1 is what we need to sub in. So we're going to get minus 1 cubed minus 2 lots of minus 1 squared, which is minus 2 lots of 1, which is minus 2, minus a plus b, and that equals 28. So if I add 1 and 2 to both sides, it's 31. So I'm going to get minus a plus b equals 31. To make this easier, I'm going to times everything by negative 1, so it becomes a minus b equals negative 31. Have I done this right? Let's double check. Minus 1 cubed is definitely minus 1. Minus 1 squared is positive 1, times 1 minus 2 is minus 2. A times minus 1 is minus a. B is that. Remainder is 28. Yeah, seems legit. 28 add 2 is 30. Add 1 is 31. So times. Okay, yeah, fine. No, just double checking. Right, okay. So when I add these two together, the b's will cancel. 2a add a is 3a. B's cancel. 1 add minus 31 is minus 30. Divide by 3, a equals negative 10. If a equals negative 10, then 2 lots of a is minus 20 plus b equals 1. So it looks like b equals positive 21. So there's my final answers for part A. For part B, show that x minus 3 is a factor. Okay, so if x minus 3 is a factor, that means I need to let x equals to 3 and show that when I substitute that in, it gives 0 for f of x. So 3 cubed minus 2 lots of 3 squared plus a, which is minus 10 lots of 3, plus b, which is 21. I need to show that equals 0, and this is when f is having an input of 3. Okay, so f of 3 will give 3 cubed is 27, minus 2 lots of 3 squared is 18, minus 10 lots of 3 is 30, plus 21 equals 0. 27 add 21 is 48, minus 18 minus 30 is negative 48. This clearly equals to 0, job done. Okay, so therefore x minus 3 is a factor of f of x dosh. Okay. Right, now I think I've talked about this in a previous video. I'm not so sure anymore. I think I might have talked about it in my year 13 class. But now we're going to be looking at partial fraction decomposition. Okay, what on earth does that mean? Well, okay, let's cast our minds back to GCSE, year 10, year 11 stuff. Suppose I've got something like this. Suppose I've got 2 over x and I want to add 3 over x plus 1. Okay, well just like how we do 2/3 plus 4/7, we need to get them, we need to get them over a common denominator. And since 3 and 7 are not only prime and they're co-prime, well, they aren't necessarily co-prime, but 3 and 7 have no common factors, so we've got to think of the lowest common multiple of 3 and 7. And we just times 3 by 7, so that's 21. So we think, what have I got to times top and bottom here to get 21 on the bottom? Well, that's 7 top and bottom, so that's 14. And what do I have to times top and bottom here to get 21 on the bottom? Well, that's 3, so that's 12. So after a little thought, that becomes 26 over 21. And if you want to go right back to year 7, then that's 1 and 5/21, if that's how you pronounce it. And the same rules work for algebraic fractions, right? So we've got an x on the bottom there, we've got an x plus 1 there, they clearly have nothing in common, so we're going to have to multiply x plus 1 top and bottom here, and we're going to have to multiply x top and bottom here. So x plus 1 top and bottom here, and x top and bottom here. So over a common denominator, this is going to be x lots of x plus 1 plus something over x plus 1. And then we're going to have 2 lots of x plus 1 plus 3 lots of x. And now if you've done this right, look, if you've done this right, then you should be able to go bosh, 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 cancel top and bottom, and you're left with the original question. Now we want to kind of uncancel it to make this work. Okay, so now we can just jump straight to the answer. And that is x times by x plus 1, and then we're going to have, think about it, 2 lots of x and 2 lots of 1, which is 2x plus 2, plus the 3 times x, which is 3x. And if you tidy all this up, 2x plus 3x will give a 5x, and we'll have a plus 2 on the end, and that's done. That's a terrible 2. That's a better 2. Okay, so my final answer for this would be 5x plus 2 over x times x plus 1. And you can't simplify that anymore, I'm afraid. That's as simplified as it gets. The top doesn't factorize, and even if it did, it doesn't have any common factors with the bottom, so you just have to leave it like that. Okay, so arithmetic with fractions goes from fractions that are, they're separate to joining the fractions. Now, these fractions that are separate are what we call partial fractions. They're breaking it into parts. We've got this quantity over here, and now what we're going to be doing is we're going to be reversing this process. I.e., if I gave you something like, let's say 1 over x plus 2 times by x plus 3, could you break that up into fractions involving x plus 2 and x plus 3 in the denominator? That's what we're talking about here. Okay, this is really easy to do. Rule number 1 is the numerator must be of an order smaller than the denominator, and it has to be the largest possible. Okay, so what does that mean? It means if I've got x plus 2 on the bottom, like so, this is x to the power 1. That is the highest power of x. So I can't have an x to the power 1 on the top. That's the same order. It has to be smaller. So I need an x to the power 0 or smaller. And I want the largest one. So clearly x to the 0 is just a constant. So we'll call that a. By the way, if this was 1 over x squared plus 2 times by x plus 3, so this was an x squared, the biggest power of x that I could fudge in there would be x to the 1. So I'd have to consider a linear term, ax plus b on the top there. And more than happy to go through an example of that, but I'm hoping I go through 1 or 2 examples, we'll get it. So the numerator must be an order smaller than the denominator. That's key. And the easy way of checking that is check the powers. The next thing we have to do is consider repeated factors and include every multiple. Okay, what do I mean by repeated factors? Well, at the moment I'd have something like this, a over that, and then this would be x plus 3. It'd be a different constant of x plus 3. But suppose this was an x plus 3 all squared. Well, then I'd have to include a different constant over x plus 3 all squared. And let's expand this. If this was an x plus 3 all cubed, then I'd need a different constant over x plus 3 all cubed. And you just have to keep going depending how that power is, because it's repeating the factors. Now you're probably thinking, okay, Pope, why is it that you just told me in the previous one that it must be smaller, the numerator must be of an order smaller than the denominator, and it must be the largest possible. But if we were to expand this, then we'd have x squareds on the bottom. Why don't we have linears on the top here and quadratics on the top here, and so on and so on? Why is that the case? Well, the special example is we're going to have to ignore that rule for factors, or not factors, we're going to have to ignore it for repeated factors, and it should only be ones that can be factorized. So the whole point is if it's repeated factors like x plus 3 cubed, say, then that technically has been factorized. I mean, x plus 3 cubed is going to be x cubed plus, and then 3 choose 1 is 3. So I believe that's going to be a 9 x squared plus 3 choose 2. It's going to be 3 times 3 squared. It's going to be a 27 x plus 81. Is that right? Let me just double check that. Pretty sure it is. I don't think my no, 3. No, that's going to be a 27 as well. So if I expand x plus 3 cubed, I'm pretty sure it's going to be x cubed plus 9x squared. Yeah. So the point is that this thing here you'd write it, it was technically that. This can be factorised down to x plus 3 all cubed. So it's technically this linear polynomial repeated. So you've got to factorise it first, and then it's the unique factors in the denominator. Okay, so let's cut to the chase. Let's ignore this cubed for a second. So that we ignore all these other terms here, and let's suppose I want to actually solve this question here. I.e., how can I write 1 over x plus 2, x plus 3 as that? Okay, well, there's a mixture of methods. So I'm going to go through both, obviously. So let's change this to a different colour so it's more obvious. Okay. So first thing we do is we're going to multiply by the denominator. So if I multiply by x plus 2, x plus 3 both sides, the left-hand side is going to be 1. The right-hand side, well, is actually going to be a lots of x plus 1. Because if you think about it, if I multiply it by x plus 2, then that will cancel with the denominator. And b, oh, x plus 3, you silly boy. And then b, would, the next term would be b lots of x plus 2. Okay. Now, there's two ways of finding out for a and b here. We can either compare coefficients, or we can use substitution and elimination. Now, there's other ways of doing this as well. Black pen, red pen does it pretty well. I can't remember how he does it. The reason why I was against it so much is because it's too abstracted and they almost treat it like a trick, and I just get the feeling that not they have forgotten what they're doing, but I just feel like for someone that's just doesn't really know what's going on with maths, that they'll just learn tricks and not really understand what it is they're doing and why. But I mean, you're more than welcome to have a look at. I mean, they're great videos. I mean, he does so much good stuff. Black pen, red pen. It's worth a look at. So I don't know. Let's look at comparing coefficients. So how would that go about? Well, let's expand the right hand side. So we've got 1 equals ax plus 3a plus bx plus 2b. Now, key points. If I look at the amount of x's, there are no x's on this side, and there is an ax there and there's a bx there. So that must mean 0 x's on the left must equal a plus b lots of x's on the right. Next up, if I compare the constants, which I'll call k, then I've got a 1 on this side and I've got 3a and 2b on this side. So that means that 1 must equal 3a plus 2b. Okay, well, it should be pretty obvious that this is a pair of simultaneous equations to solve. If I multiply the top one by 2, I'll get 2a plus 2b also equals to 0. And then if I subtract stuff, 1 minus 0 is 1. 3a minus 2a is also a, and 2b minus 2b cancels. So I get a equals to 1. Now if a equals to 1, 2a plus 2b equals to 0, or just a plus b equals to 0. So that's clearly going to give that b is equal to negative 1. So now I am supposing that 1 over x plus 2 times by x plus 3 equals a, which is 1 over x plus 2, minus b, which is minus 1. Now, I could, I could technically say plus and then make that a minus 1, but that's clearly the same thing as minus the positive, and then this is x plus 3. Okay, this is true. And you can do the calculation yourself, i.e. times by x plus 3 top and bottom there, times by x plus 2 top and bottom there. Be careful with this negative sign, and you'll get the answer. Okay, let's suppose I want to do this by substitution and elimination. So if I look at the original thing, can I substitute x? Can I substitute in a particular value such that x plus 3 equals 0? Well, if x plus 3 equals 0, then x equals negative 3. So this becomes 1 on the left-hand side, because 1 is still 1, we've chosen x, so the a term disappears. And so now we're left with b lots of minus 3 plus 2, which is minus 1. So we've now got minus 1, b equals 1, so b equals negative 1, which agrees with our comparing coefficients way. Similar reason or logic, what must x be so x plus 2 equals to 0 to eliminate for b? Well, clearly x must equal to negative 2. So this is going to give on the left-hand side 1, and then a lots of negative 2 plus 3 is 1, and then we chose x to be negative 2, so this term disappears. So we're going to get 1a equals 1, which clearly gives a equals to 1, and then this still agrees with the other way. Yeah, pretty powerful stuff. What you have to understand is that, especially with repeated factors, that you're going to have to use kind of a mix and match method, i.e. a little bit of both. Now, to give an example of repeated factors, I don't know, let's say with this previous example, I'd stuck to my guns, and one of them was squared, for example. I mean, I could make it cubed, but you're going to get the idea after a while. So, okay. So let's say it's the x plus 3 that's being squared for no reason. I could have made the x plus 2 all squared. So this is going to be some a over x plus 2 plus b over x plus 3 plus c over the x plus 3 all squared. Okay, right. So what we're going to have here? Well, same rules, we're going to multiply it by the denominator. So essentially we're always left with the numerator on the left hand side, so this becomes 1. But then you're going to have to think very carefully what the right hand side becomes. Well, it's going to be a lots of everything else that's not included by the bottom bit. Well, that's going to be x plus 3 all squared, plus b lots of, and now everything that is not x plus 3, or rather one lot of it, well, that would only cancel with one lots of the x plus 3 squared. So you're actually going to get x plus 2, but then one left over x plus 3 going on here. And then plus c, well, I've already factored in x plus 3 all squared on the bottom. So the only thing that's going to be left over is going to be the x plus 2. You can multiply both terms over and see that stuff cancels. I'm just going to trust that you can do that. Okay, now for this, let's point a few things out. Why won't substitution necessarily work? Because let's suppose I make the substitution x equals to minus 3 so that the a disappears. Well, because the b also has x plus 3, that'll disappear, and c will work, i.e. we'll get something for c. So if x is minus 3, I'll have 1 on the left-hand side, and I'll have c lots of minus 3 plus 2, which is minus 1. So we'll get quite quickly and nicely that c equals to negative 1. Okay. Now, suppose I want to eliminate for c. Well, what must x plus 2 be equal to 0 mean that x is? Well, that means x equals negative 2, same as before. But the b also shares a plus 2 there, so the b is going to be eliminated as well. So when you do that, you're only going to be left with a. So you're going to get 1 equals a lots of minus 2 plus 3, which is 1 squared. And if 1 squared times a is 1, then clearly a equals to 1. Now, here's where I'm talking about, where I said you're going to have to use a hybrid method of comparing coefficients and substitution elimination. Because now look very carefully. This middle term has got something in common with everything else. So there is no unique substitution to isolate that term on its own, i.e. there's no substitution that will get rid of the a and c together. So we're kind of at a loss there, but now we can switch over to our other method, so comparing coefficients. And this is actually really easy at this point because, well, if I expand this, the highest power is going to be x squared and x's and numbers. If I expand this, it's going to be x squared, x's and numbers. And if I expand this last term, it's just going to be x's and numbers. So I might compare the x squared terms. On the left-hand side, I've got none. On the right-hand side, I don't have to expand this fully. I just know I'm going to have 1 lots of x squared, but times by a. So I'm going to have a lots of x squared there, plus, And then for the second term, well, I've got the same thing again. I'm just going to have an x squared times by b, so it's going to be a b. Now I know that a is 1 already, so then 1 plus what equals to 0, that means b equals negative 1. So actually, this actually wasn't actually too hard. I can claim that something like this will happen. Let's get rid of these. So what am I saying? I'm saying a was 1, so that will go a 1 there. B was negative 1, so that'd be a minus 1 there. And C was negative 1, so that's there. And that's it. That is a true thing. And you can, do that for yourself. My only final comment to make things a little easier is suppose you've got some A's, like a 2/3, say, and a B equal 3/5. Let's say you're doing some function of x and you suppose it's some a over x plus 2 plus b over, I don't know, x minus 3. And you get something like this. You get a and b are fractions. And you're probably thinking, oh, that's a bit weird. So am I supposed to put 2/3 over x plus 2, sorry? And am I supposed to put 3/5 over x minus 3? What? No. Well, that's not technically wrong, but the way to get around that is, see what I'm going to do with these numerators 2 and 3. I'll put them up the top, so 2 and 3. And then on the bottom, I'll have x plus 2 and x minus 3 still. So there's my numerators as before. But now look to see what I do with the denominators 3 and 5. I'm going to put the 3 there and 5 there, like so. It's just neater if you do it that way. Yeah. If I was to do one more example, I don't know. Let's say, let's have a final one. Let's make it quite small. Let's say I was to have 3 over, and then let's say I've got x minus 3 times by, I don't know, something that doesn't factorize, x squared plus 2x plus 2. Okay, now this quadratic doesn't factorize, so that means this needs to be broken up into some constant over x minus 3 plus, and then because this is a quadratic that cannot be factorized or broken down anymore, I'm going to have to consider the largest order polynomial that's smaller than a quadratic. So that's clearly a linear one, so I'm going to have to consider bx plus c. Okay, well, same deal as before. I'm going to multiply both sides by the denominator, so I'm left with the numerator, to give 3 on the left-hand side. And on the right-hand side, we can have a lots of the other factor, which is x squared plus 2x plus 2. And on the right-hand side, we have bx plus c, lots of the other factor that wasn't in its denominator, which is x minus 3. Same deal. We can use substitution or comparing coefficients. I'm going to do comparing coefficients, just for the lols, I guess. So if I look at the x squared coefficient, I've got none on the left-hand side. I've got an a there, and I'm going to get a b x squared there. So I know a plus b equals to 0. If I look at the x coefficient, I'm going to have a times by 2x. I've got 0 on the left-hand side. I've got 2a on the right-hand side. I'm going to have a minus 3bx popping out here. I'm going to have a plus cx there. And then if I look at the constant term, I've got 3 on the left-hand side. I've got a times 2, which is 2a. And I'm going to have a c times minus 3, which is minus 3c. Now, if you wanted to make this really easy, I'm going to use a substitution and let x equals to 3, because I know that this whole term on the right-hand side will disappear. When a is 3, I'll have 3 on the left-hand side because there's nothing to substitute in. And then I'll have a lots of 3 squared is 9, plus 2 lots of 3 is 6, plus 2. 9 plus 6 is 15, plus 2 is 17. So 17a equals to 3. So it looks like a equals 3/17. Now that a is 3/17, hopefully you'll see that b is just the negative of that, minus 3/17, because they have to equal to 0 here. And then to work out c, well, I can substitute into the bottom one, I suppose. So I've got 3, oh dear, which is 51/17. 3 10s are 30, 3 7s 21. Yep, equals 2 lots of a, which is 6/17 minus 3c. Okay, well, okay. 51 minus 6, I believe, is 45/17. That's minus 3c. If I divide by 3, it looks like c equals to negative 15/17. So, okay, here's an example of where my doodahs are not particularly nice. So, how would I use my coefficients here that I've just found back into this original thing up here? Well, first of all, it's key to note that they're all over 17. So I can put 17 outside in brackets, like here and here. And then a was 3/17, so that needs to be a 3. B was minus 3 and c was minus 15. So now because they're both negative, I'll put a negative here. So b will be minus 3, so that's just a positive 3, and c was minus 15, so that will just become a plus 15. And in actual fact, 3x plus 15 factorizes to 3 lots of x plus 5. And yeah, that's it. That is the partial fractions decomposition of that horrible fraction to the left. Now, you're probably thinking, oh God, why do we have to do this stuff? You're just making fractions needlessly complicated. To be honest, you had one fraction here which was nice, and now you turned it into 2. That doesn't make sense. Why are you doing this? And the short answer is that it's quite useful to be able to go between both. For example, if I asked you to integrate this with respect to x, that's quite a challenging integral to do mentally, whereas to integrate these two things is actually a doddle. It's actually a lot easier. And we'll talk about that when we come to integration techniques. So yeah, it's almost like a precursor to integration. It's also really good for checking to see upper and lower bounds of sums, series, that kind of thing. It's another tool in your tool belt. It's really useful to have. So partial fractions decomposition, it's a staple. You need to know how to do it. So let's have a look at a couple of examples. So pause the video, give it a go yourself if you think you can. I'll go through it in a second. Okay, given that f of x can be expressed in the form below, which it can, find the values of b and c and show that a equals to 0. Right, okay, so same deal. If I take this f of x and multiply by the denominator, I will get 27x squared plus 32x plus 16, and this equals the right-hand side, which is this stuff. Now, one of the 3x plus 2's will cancel, so this will be a lots of the other 3x plus 2 multiplied by 1 minus x, plus b lots of, now there's a 3x plus 2 all squared on the bottom, so I'm not going to have any of those, so that's just going to be a 1 minus x, plus c lots of, and well, the 1 minus x would cancel, so I'm left with the 3x plus 2 all squared. Okay, because there's repeated factors, probably going to do substitution and then compare coefficients at the end to check. So clearly, to eliminate the a and the b, then I want x to equal 1. So when x equals to 1, I'm going to have 27 lots of 1 plus 32 lots of 1 plus 16. So 27 plus 32 plus 16 equals c lots of 3 lots of 1 plus 2, which is 5 squared. Tidy this up real quick. 25 plus 32 plus 16 will give 73. So it looks like 25c equals 73. I definitely copied that down right. It seems a bit weird. 27. Oh, I've done the wrong thing. 27 plus 32 plus 16. is 75, silly boy. Right, so that means C equals to 3. Nice, that's one of them. To work out B, well, that's going to be quite straightforward as well, because to get B on its own, I just have to substitute in x equals minus 2/3. So if x equals negative 2/3, then the A and C will disappear. So we have got 27 lots of negative 2/3. I'm going to use my calculator here, I can't be bothered to type all that in. 27 times minus 2/3 squared, yep, plus 32 brackets negative 2/3 plus 16. So the left hand side becomes 20 over 3, and this will equal B, which is 1 minus 2/3, which is 1 plus 2/3, which is 5/3 of B, and it looks like B is just going to equal to 4. Okay, so I've now got B and C. Let's find out what A is. Okay, for the last trick, I'm probably just going to compare coefficients. And let's take the constants for no reason. I've got 16 on the left-hand side. I've got A times 2 times 1 there, which is 2A. And then I'm going to have a B there, which is a plus a B. And then for here, I'm going to have this 2 squared, which is 4 times C, so I'm going to have plus 4C. B is 4, so that's plus 4. 4C will be 4 lots of 3, which is 12. So I have 2A plus 4 plus 12 equals to 16. 4 plus 12 is 16. So I have 2A plus 16 is 16. So then 2A equals to 0, which means A equals to 0, and we're done. So the value of B is 4, the value of C is 3, and A does equal to 0. So if I was to express f of x in that form, since A is 0 and B is 4, then this thing could be written as 4 over 3x plus 2 all squared plus C, which is plus 3 over 1 minus x. Okay, lovely jubbly. Right, next one. Find the values of the constants A, B, and C such that the following. Okay, now, interestingly, if you want to pause this and have a go for yourself, there's one more intermediate step that I've glossed over a little bit. And that is what happens when the numerator's order, which is to the power of 2 here, is the same or larger than the denominators. When that's the case, then you have to do algebraic long division first. And that should be a clue by the constant term down here. So what I need to do is 9 plus, well, actually, let's get it the right way around. I've got 4x squared plus 0 lots of x plus 9, right? You've got to be really careful to include every descending power of x. And then this will be negative 4x squared plus 0x plus 9. So how many minus 4x squared is going to 4x squared? So that'd be negative 1. And then minus 1 times all this lot is going to be 4x squared plus no x's. And minus 1 times 9 is minus 9. This all goes over here. That and that cancel. That and that cancel. 9 minus minus 9 is 18. So immediately A equals to negative 1. And now what we need to do is show that this decomposition comes from 18 over 9 minus 4x squared. Okay, because the remainder is 18. Right. Okay, so 18 over 9 minus 4x squared is going to be some constant over 3 plus 2x plus another constant over 3 minus 2x. I hope you can see that's from a difference of 2 squares by factorising the bottom. If I multiply by the denominator both sides, I'll get 18 on the left-hand side. I'll get A lots of 3 minus 2x, and then I'll have B lots of 3 plus 2x. If I let x equal to positive 3 over 2, then the A cancels. So then I'll have 6b equals to 18, which means b equals to 3. And if I let x equal to negative 3 over 2, so that the b disappears, I'll have the same deal of 6a equals to 18, because minus 2 times minus 3 over 2 is plus 3. 3 plus 3 is 6. 6a is 18. So a equals to 3. So in actual fact, this whole thing will boil down to minus 1 plus 3 over 3 minus 2x plus 3 over 3 plus 2x. Lovely jubbly. Okay, so a couple of things I might have glossed over. The power of the numerator has to be smaller than the denominator, right? Was that obvious? Well, I suppose so. I mean, like if I wanted to say 17 over 4, then you should have really broken that down into 4 1/4, and then it's that quarter you should have decomposed into maybe halves and quarters, maybe. Whoa, geez, yeah. You know, and in this case, it would be 0 halves plus 1/4. Is it obvious? Probably not. But yeah, you don't want improper fractions, i.e. you don't want where the order of the numerator is higher than the denominator. Yeah. So the order on the bottom has to be higher. So in this case, because they were the same, you need to do algebraic long division first. And suppose, right, what you don't want to do is you don't want to do 9 minus, was it 9 minus? You know, you want 9, right, if you have 9 plus 4x squared and you divide that by 9 minus 4x squared, this isn't going to work. What you have to do is arrange them in descending powers of x's, and you have to include everything. So say, for example, I wanted x cubed plus 6 divided by x squared minus 1, then I would have to do x cubed plus no x squareds plus no x's plus 6 divided by x squared plus no x's minus 1. And now you can do it, right? Yeah, you just have to do it that way. I guess you could see it as numbers. I mean, if you have 100 on the top plus a 1, you don't just do divided by, let's say, 3 10s and a 2. Well, you could have 3 10s and a 2 on that side, but you don't just put 1 1 for 101, because that's the hundreds and that's the 1. You've got 0 10s in the middle, right? You just, there's a little bit of an analogy there, but you just got to be really careful. To be honest, if you're struggling with this stuff, you can always use Wolfram Alpha, and that will always pop out some answers for you. But yeah, algebraic long division, you just have to get it right. Descending powers of x, highest power first, and make sure you include every single power of x down. And that's it. So hopefully a fairly short one. Toodaloo.